For this lesson, we're going to be taking a look at the concept of continuity, and this is going to tie in quite closely with what we've talked about so far with regards to the limits. We're going to be using the limits to help us define continuity and to decide whether or not a function is continuous. So first of all, when we talk about continuity, usually what we're going to be talking about is going to be at a particular x-coordinate. So all x-coordinates make up the domain of the function, and so we're going to single out a particular value. Typically this is referred to as a, or an actual value, an actual number. And so there are two conditions that must be met for a function to be continuous. The first condition is that the limit at x equal a exists. So as we get closer and closer to a, then the limit has to be a value. And this is worth pointing out because we've used this limit before and we've allowed ourselves to have limits that were equal to positive or negative infinity. This has to be an actual number, so this must be a value, and it absolutely cannot be infinity. Okay? So this has to be a concrete value in the limit. And in general, that means that both our left and right side limits have to exist and they have to be equal. Now I'm going to discuss this idea of having both the left and right side limits. I'm going to give you an example on the next page to show you that that's not always the case. This is generally the case, but it is not always the case. So we'll take a look at that in a moment. But in general, the limit has to exist at x equal a. The other thing, and this is what differentiates continuous from just taking a limit, the other thing is the actual value at x equal a has to match the limiting value. When we looked at limiting values, it was possible to have a limit even if the value itself wasn't defined at that point. So for example, a hole. But for continuity, when we look, we actually have to be able to go stand at x equal a. We can't have a thing like a hole there. Even if we're approaching it, we have to actually have a concrete value at the actual location. These two requirements combined as a single statement look like this. So essentially what we're saying, the limit as x approaches a of f of x has to be equal to the value of the function at a. A little side note, all polynomials are continuous for all real numbers. In other words, they're continuous on their entire domains. And that's just a property of polynomials. Polynomials never have asymptotes. Polynomials never have holes. They have domains that go from negative infinity to positive infinity. So all polynomials are continuous for all values. Okay, now let's take a quick look. I don't want to drag this out, but let's take a quick look at this exception that I was discussing. I consider this to be an extension of what we're doing. You generally are not going to run into this, but students who give some thought to their work will sometimes come across situations that look like this. So it's worth mentioning it in advance, even if you have to come back here and take a look at it again. So we can have a couple of things. One of them is some functions naturally have restrictions on their domain. And that's the example I've given here, which is the radical function. The radical function's domain goes from 0, and it includes 0, to positive infinity. Sometimes, in other cases, we're only interested in some limited part of the domain. So we may actually place a limit on the domain ourselves. So we might say that we only want the domain between 3 and 20, for example. So what we're saying is I don't want any values less than 3 or any values greater than 20. In either of these cases, we have to consider an exception to our rule on the previous page. And so I'm going to use the radical function to illustrate that exception. So the question that gets asked here would be, is the radical function continuous at x equals 0? Now, your first instinct, especially if you use this definition, and the idea that both the left and right side limits must exist, Well, you would immediately exclude this. You would say, well, no, that's not, it's not continuous because the limit from the left does not exist. There is nowhere over here. I can't take the limit from the left of 0. The function doesn't exist to the left of 0, so that means I can't find the limit. To the right, everything works just fine. I trace back along this line. As I get closer and closer to 0, I close in on 0 itself, and the function has that value. I can sub in x equals 0 into the original function. So this part works just fine. So now the question becomes, how do we deal with that? But because this value to the left of 0 is not even part of the domain, when we talk about continuity, we're generally talking about between, or we're generally talking about values that are on the domain of the function itself. Now this raises all sorts of questions. Well, what about holes? Because holes aren't part of the domain. Those are restrictions, etc. So I'm going to ask you to think about this just in terms of limits to the domain, to the edges of the domain. If those limits at the edges are due to asymptotes, those are going to take care of themselves anyway, because those are infinities. But in the case of something like this, where it actually does approach and meet that value, then we're going to say that this is not a requirement because this limit is not part of the domain. And so in this case, we are going to say, yes, this actually is continuous on its domain. It is continuous on the domain 0 to infinity, including 0. Okay, now generally we're not going to be looking at things that are running up against the edge of domains. We're going to be asking about, is a function continuous at a particular point? And if we identify that it is not continuous, then that means it's going to have some sort of discontinuity. There are 3 types of discontinuities we're going to be looking at. So a jump discontinuity we will see most readily in a piecewise function. A removable discontinuity, the removable part means when you've done something like this, x times x minus 1 over x minus 1, the removable discontinuity means I have divided out some common factors. That results in a hole. And then an infinite discontinuity would be a vertical asymptote. And that one is probably the one that we're most comfortable with and is most obvious to us. Although, as you're about to see, a piecewise function discontinuity is quite obvious as well. So, our first example here, identify where each of the following functions is discontinuous and state the type of discontinuity. And I want to do more than just identify. I want to show that it's discontinuous at that value. So in this case, we take a look and we suspect that we have a discontinuity at x equal negative 1. And so the way we're going to check that is we are going to take the left-sided limit, the right-sided limit, and we're going to test the function itself at that value. So we take the limit as x approaches negative 1 from below of, and I'm just going to call this f of x, and the limit as x approaches negative 1 from below is going to be along here approaching this value. So it looks like it's approaching the value of 2. Then I'm going to take the limit as x approaches negative 1 from above of f of x, and that is equal to, and now I have to go past negative 1, I have to go to the right of negative 1. That puts me on this part of the function of the graph, and that's approaching the value of positive 3. So we can already see the left-sided limit and the right-sided limits don't match each other. So just for that reason alone, this limit does not exist. We have a left-sided and a right-sided limit, but they don't match. And then the final thing we really should check would be, we would check the function value at negative 1. And the function value at negative 1 is that value right there. You can see we have a solid dot there. And so it's equal to 2. And so therefore f of x is discontinuous at x equal -1. And what kind of discontinuity is this? This is known as a jump discontinuity. And not particularly creatively named. It is called a jump discontinuity because as we trace the function on the graph, we get to a certain point and then the function resumes after jumping to a brand new y value. So the jump occurs in the y value. Identify where each of the following functions is discontinuous and state the type of discontinuity. And here we take a look at it. We can see we have two vertical asymptotes. And as I mentioned at the beginning, vertical asymptotes are always going to result in a discontinuity. And the reason for that is because of the infinities involved. So even though, so let's take a look. Let's start off looking at x equal -4. And so we'll take the limit as x approaches -4 from below of f of x. And what is that equal to? So starting from below, so to the left of -4, I can going up and up and up, and so that is equal to positive infinity. Then I take the limit as x approaches -4 from above of f of x. And from above, that is, so the first one I already did was that. Now I'm going to be tracing down along this way. That is negative infinity. So first of all, these two limits do not match, so I know it is not continuous. And I also know that f of -4 itself, am I allowed to look or am I allowed to stand at -4? I am not. So, well, f of -4 does not exist, or actually I think I'd probably prefer here if we said f of -4 is undefined. But in either case, what we don't have is these things are not all equal to each other. And in particular, because f of 4 is undefined, it can never be equal to anything. So it is not continuous, and in this case, we have a vertical asymptote, which is an infinite discontinuity. So therefore, we have an infinite discontinuity at x equal -4. Now, what about our other vertical asymptote, which is at 2? So at x equal 2, we're going to test the limit as x approaches 2 from below of f of x. As I approach 2 from below, that would be along this part of the line. So I am approaching positive infinity. I'm going to approach 2 from above of f of x. And that's also going up here towards positive infinity. And so this ties into our previous lesson, which means this limit exists. The limit as x approaches 2 of f of x is equal to positive infinity. So the limit itself exists. Whereas over here, the limit does not exist. Because even though they're going to infinities, they're not the same infinity. One is positive and one is negative. Now, in this case, the fact that the limit exists doesn't actually matter because f of 2 itself is undefined. And so because it is undefined, I don't care whether this limit exists, whether it's positive or negative infinity. This cannot match anything. So therefore, once again, we have an infinite. Actually, I might as well just go ahead and add that into my, we have an infinite discontinuity at x equal 4 and x equal 2. Because in both cases, it is an infinite discontinuity. Identify where each of the following functions is discontinuous. In this case, we have a linear, but we have a hole here at x equal -4. And so we are going to be testing x equal -4. We'll take the limit as x approaches -4 from below of f of x, and that's going to be this part. We are approaching the value of 2. We're going to take the limit as x approaches -4 from above of f of x, and that's this part approaching, once again, the value of 2. So these two things together means the limit exists, and so we can say the limit as x approaches -4 overall is equal to 2, but f of -4 itself, that is a hole. And so once again, we end up with undefined at the actual value. And so because this is undefined, I don't care that the limit exists. I don't care if it's a finite number like 2 or if it's an infinity. The bottom line is, therefore, we have, and we go back and take a look at our terminology. In this case, in the presence of a hole, we have what's known as a removable discontinuity. So therefore, we have a removable discontinuity at x equal -4. And that's it. So we're really just extending what we did with limits. We're still making use of the idea of limits and just taking it a little bit further. This idea of continuity is going to play a big role as we move forward from this point in the course, as we start to get into the actual idea of some of the tools of calculus and taking derivatives.